This video is for my EE304 LabView project. It revolves around integrating LabView and MyDeck programming with the basic circuits lab. In my case, Thevenin and Norton equivalents. Okay, starting off with the pre-lab, we were asked to find the Thevenin voltage, Thevenin resistance, and the short circuit current for this circuit in particular. I started off by doing a source transformation for the 9-volt independent voltage source to a 6 milliamp independent current source. The 1.5 and 5.6 kilo ohm resistors are in parallel, so we find the equivalent resistance of that, which is 1.18 kilo ohms. Then you just do another source transformation, transforming that 6 milliamp current source to a 7.08 volt voltage source, adding the two resistors in series. Then you do another source transformation from the 7.08 volt voltage source to a 3.25 milliamp current source. The 2.18 kilo ohm resistor and the 2.2 kilo ohm resistor are in parallel, so you find the equivalent resistance of those, which is 1.1 kilo ohms. Then it's one more source transformation, changing the 3.25 milliamp current source to a 3.575 volt voltage source, adding those two resistors in series, the 1.1 and 4.7 kilo ohm resistor, which are 5.8 kilo ohms, and that is your Thevenin equivalent circuit. Do another source transformation for your Norton equivalent circuit, which is 6.2 milliamps. So your short circuit current is 0.62 milliamps, your Thevenin resistance is 5.8 kilo ohms, and your Thevenin voltage is 3.575 volts. This is my breadboard setup. The yellow wires are in the positions of A and B, and the green wires are leading to the battery. And this is the setup for when I was measuring the resistance. Using the digital multimeter, the open circuit voltage results were 3.8 volts. The experimental results for Thevenin resistance was 5.72 kilo ohms, and the short circuit current was 0.66 milliamps, all under 10% error. Now on to the actual lab portion. The instructions for the lab portion say to solve this circuit by hand first for the open circuit voltage, the short circuit current, and the voltage V0, which is across the leads A and B, which aren't visible in the picture, but they're there. There's our circuit at the top. The first step is to remove the load resistance, which in this case is 4.7 kilo ohms. And once we've done that, we can move on to finding out what the voltage is across the 2.2 kilo ohm resistor. And we simply just use a voltage divider for that, which is 9 volts times 2.2 kilo ohms over the sum of 2.2 and 1.5 kilo ohms, which happens to be 5.35 volts. And from that we can determine what the dependent voltage source voltage is, which is just half of that, 2.68 volts. And then once we do that, we can use Kirchhoff's voltage law to sum the voltages around the loop, the outer loop. That's 9 volts, Vx, and also the dependent voltage source, and the open circuit voltage, which are all, the sum of all of them are equivalent to 0. And we find that the open circuit voltage is 6.33 volts. Then we find the short circuit current, which we use Kirchhoff's voltage law again to find, which is to find Vx, when Vx equals 18 volts, which means we use Ohm's law to find I1, which is 8.18 milliamps. Then we plug that equation into the equation for I2, which is also the short circuit current, and that's 2.18 milliamps. So in order to find the Thevenin resistance, we just divide 6.33 volts by 2.18 milliamps, and that's 2.73 kilo ohm. There's the Thevenin equivalent circuit with a load resistance thrown back onto it, and there's the Norton equivalent circuit. And just use voltage division to find the V0, which is 4 volts. Here's the breadboard setup. The green wires were used for the battery voltage, which is 9 volts. The yellow wires were used for the dependent voltage source output, and the orange wires were used for the analog input for that dependent voltage source. The red wires were used as leads to calculate voltage and current across the open circuit, and the top voltage there is Vx, and the bottom is the dependent source output. Again, this is just the outputs on the digital multimeter for current and voltage across the open circuit. And this is the setup to measure the load voltage across the 4.7 kilo ohm resistor. That voltage turned out to be 5.16 volts.